These are our notes on waves and electromagnetic radiation. So electromagnetic radiation comes in a range of energies called the energy spectrum. Radio, microwave, infrared, visible, UV, X-ray, and gamma rays are all examples of energy waves, and these are forms of traveling waves. And we measure wavelength with this sign right here, and we measure it from crest to crest or valley to valley. Waves are characterized by their wavelength and their frequency, which is the number of times a like point, so for example a crest, passes a stationary point at a given time. Wavelength is usually measured in nanometers, and frequency is usually measured in hertz. Wavelength and frequency are related by the speed of light, so we know that the speed of light is 3.00 times 10 to the 8 meters per second, and we measure it with wavelength times frequency. This is an inverse relationship, so if I have a low frequency, that means that I have a high, or if I have a low frequency, that means I have a long wavelength. If I have a high frequency, that means I have a short wavelength. So high frequency is a short wavelength, low frequency is a long wavelength, and we will review this a lot. So here's an example of, we've got long wavelengths and low frequencies, and here we have shorter wavelengths and much higher frequencies. So that's what we mean by that. So here's another example with colors. We've got our visible spectrum here with Roy G. Biv, and just an example of the size of the wavelength that you would see. So visible light ranges from 400 to 700 nanometers, and we know that it separates into different colors. When we see all of these combined, we perceive white light. So if we're looking at this, which has a higher frequency, red or violet, as you're just looking at these energies? So hopefully you answered correctly that violet has a higher frequency because it has a higher energy. So again, if I have a long wavelength, that means I have low frequency, which also means I have low energy. So if I've got something with low energy, it's not going to have a very fast wavelength. Short wavelength, high frequency, high energy, these guys are going to pass a given point much, much faster, thus they are high frequency and high energy. So here's just another example of our electromagnetic spectrum here. We've got the different wavelengths in meters and showing our visible light and the general wavelength in meters there. So atom line emission spectrum, so why are we talking about electromagnetic radiation in chemistry? Well, we want to talk about ground state and excited state. We want to apply the Aufbau principle to this, and then we're going to apply why we see colors. And so when we're talking about maybe like fireworks, for example, so ground state means that it's just the lowest energy state of an atom, and it's the lowest energy state of anything. We all want to be lazy. We all want to be in our ground state. It's very easy to be in our ground state. The excited state is a higher potential energy, and it takes energy, and it's more energy than the ground state. And so excited state would be like if you're like sprinting. Ground state would be like if you're just standing still. When an atom gets to an excited state, it will return to its ground state. When it does that, it will give off energy in the form of electromagnetic radiation. So understanding how electromagnetic radiation interacts with atoms has helped develop many theories about the electrons and how they are organized and how they behave in the atoms, and namely how those electrons are arranged in shells. So electrons want to be in the lowest energy level possible, but can be excited via outside energy into a higher state. When they are in their higher state, it takes energy to stay there. They don't want to be there because it takes a lot of work, and things in nature would rather exist at a lower energy level. And so those electrons in those atoms will return to their ground state. When they return to the ground state, they will release energy. So here's just a drawing. So I've got a low energy level and a high energy level. And here's just representing energy getting put into the electron. So my electron now is going to jump up to an excited state, and here we're at the ground state to start, and it's going to absorb energy, and it's going to jump up to the excited state. It does not want to stay there. Aufbau principle tells us that atoms want to be in the lowest energy level possible, so it will want to return to its ground state. So it's not happy at its excited state. When it returns to its ground state, it will release off energy in the form of light if it is in the electromagnetic wavelength that we can see. So we will be able to see the colors if it's in those specific nanometers. So here is just another atom emission model showing with all the circles instead of just lines. And so here I'm showing energy being absorbed by the electron. That electron was at the ground state. It's jumping to the excited state. So if I were to draw the emission level, I'm going to start with my electron here. I'm going to show it jumping back down to its ground state, and in that I'm going to show it releasing that wavelength of energy there. If we see color, we know that it is in the visible range of 400 to 700 nanometers. So here we're just wanting to draw the absorption model, so we have the emission model on this example. So I have my electron starting here going back down, which means I can jump over here and say, well, I know that the electron then started here and jumped out to the highest energy level. So it's going to release that once it jumps back down. So how and why is the orange and green example different? Hopefully you're able to understand that the green has a higher frequency and more energy because the green was moved more energy levels. So this was moved 2 energy levels, so it would have absorbed more energy, thus released more energy. Whereas the orange example only jumped 1 energy level, so it did not absorb as much energy, so thus it did not release as much energy. We observe colored light when a source of light only produces light of one or a narrow range of energy, so neon signs are a good example. One or more energies or colors are removed from white light by some substance that absorbs them. So for example, cobalt glass absorbs a specific wavelength and allows others to go through it. So white light, sometimes when absorbed by a certain thing, white minus red would give us green. So also this can happen when things are, when light passes through a prism, it will break up and show us the rainbow. So here's an example of energy levels and just showing us energy levels in different states and helping us with understanding how much energy would have been absorbed, thus how much energy is released. So in this example here, if I've got my energy levels, so N is representing the rows on my periodic table, my energy levels here. So I've got my ground state, my second, third, fourth, fifth energy level, and so on and so forth. So from here, I can show that the red was absorbed 1 energy shell, so it will drop down 1 energy shell. The teal is 2, and the blue is 3. So based on this, I can predict that the blue here would have released the most energy because it absorbed the most energy and jumped the most energy shells. The teal would have a moderate amount of energy, and the red would have the lowest energy, so thus a long wavelength and a low frequency. You will need to be able to read this type of graph in the future, so please make sure that if you have any questions, you come to class with those questions. Thanks for watching the notes and filling them in on your PowerPoint.